tutorial video. Hello and welcome to this tutorial video on losses of energy in pipelines. In the last video or in the last tutorial, we considered a case, an example for sudden expansion, and today we will be treating sudden contraction. Please do like this video and subscribe to our channel for more updates on this topic. So what we have here, the system that we have here describes the sudden contraction. So basically, when a fluid is traveling, the fluid represented by the blue dots over here, when a fluid is traveling from the channel 1 and it suddenly contracts to form the section 2, what happens is that a vena contracta is formed. Vena contracta. And that is basically this shape here. In section 3, a vena contracta is formed inside the pipe, and this is very important for our consideration. Assuming that the area of the first portion of section 1 is A1 and the velocity is V1, and the area of the second portion is A2 and the velocity is V2, the area in this vena contracta is AC and the velocity of the fluid in that vena contracta is VC. We can make some statements based on that. The thing is that the loss of energy in the convergence from the section 1 to 3 is small, and the main loss actually occurs in the enlargement from section 3 to 2, as if it were due to an enlargement or a sudden enlargement from area of the vena contracta to area of the second section A2. So basically, we will be considering it, the sudden contraction case will be considered as a case of the main loss is the sudden expansion from the portion of the vena contracta to the full bore or the full area of the pipe 2. So using the equation for loss of head that we derived earlier, so loss of head, the reason for this is that the contraction or the loss at this point during convergence is negligible, very negligible, compared to the loss that occurs due to the expansion from section 3 to 1. So basically, we'll be considering this sudden contraction as an expansion, a loss that is due to the expansion from section 3 to 2. The loss of head will now be equal to Vc minus V2 all square over 2g, where Vc is the velocity of the vena contracta and V2 is the velocity of the full bore of the fluid at section 2. So that is the loss of head. And now for continuity of flow, we have Q is equal to A2 V2, which will now be equal to AC VC. So we are trying to derive the expression for the loss of head that occurs when flow passes through a sudden contraction in a pipeline. Now we know that this charge Q is equal to A2 V2, which is equal to AC VC. If the coefficient of contraction, if we assume that there is a coefficient of contraction now, and we call that CC, if the coefficient of contraction is equal to AC over A2, from this discharge equation, we can easily put in the coefficient of contraction, because that will give us, if we have V2 over Vc, that will be equal to CC, basically AC over A2, which gives us CC. and we can have something of this nature to make Vc the subject of the formula. So Vc will be equal to 1 over Cc multiplied by V2. The reason we want a coefficient for this is because we may not be able to measure the velocity of the vena contractor. We will know the velocity, or we can measure the velocity at the section 2, we can measure the velocity at the section 1, but the velocity of the vena contractor is inside the pipe, so we may not be able to measure it. So we need some sort of way of knowing. So velocity of the vena contractor, of the fluid in the vena contractor, is equal to 1 over Cc times V2. Now we can substitute that in the equation above. Let me call that equation 1. Now clearing up space. So the loss of head at sudden contraction will be equal to, substituting that into the equation now, we have 1 over Cc V2 minus V2 all square over 2g. We see that V2 is common to both equations, so we can factorize that out, and then that will become V2 square over 2g into bracket 1 over Cc minus 1 also all square. And this gives us the loss of head at a sudden contraction. So now let me put this inside the Bernoulli's equation. So we have P1 over W plus V1 square over 2G will be equal to P2 over W plus V2 square over 2G. Now plus the loss of head, which is V2 square over 2G into bracket 1 over Cc minus 1 square, where Cc is the coefficient. Sorry about my writing, of contraction. Where Cc is the coefficient of contraction. We can simplify this equation further to give us P1 over W plus V1 square over 2G is equal to P2 over W plus V2 square over 2G into bracket 1 plus 1 over Cc minus 1 all square, and close that bracket. And this is an equation now when we insert it into the Bernoulli's equation. Now let us take an example on sudden contraction. Example: a pipe carrying 0.06 meter cube per second, that is the discharge Q is equal to 0.06 meter cube per second, suddenly contracts from 200 mm diameter. So D1 is equal to 200 mm to 150 mm diameter. D2 is equal to 150 mm. Assuming that a vena contractor is formed in the smaller pipe, calculate the coefficient of contraction if the, so we are asked to calculate Cc, the coefficient of contraction, if the pressure head at a point upstream of contraction is this greater than at a point just downstream of the vena contractor. So this means that P1 minus P2 is equal to over W. P1 minus P2 over W is equal to 0.655 meters. So when they say a point downstream of the vena contracta is a point upstream, that is P1, is this greater than a point downstream, that is P2. So this is the difference. We have to calculate CC. So now let us write out Bernoulli's equation for both points. So we have something like this, or the Bernoulli's equation like this: P1 over W plus V1 square over 2G is equal to P2 over W plus V2 square over 2G plus the head loss due to contraction. And the head loss due to contraction will be equal to, from the formula that we've just proven, V2 square over 2G into bracket 1 over CC minus 1. Is that right? Yes, minus 1. So by the time we get this, we can just input it into our equation, and we know that that will become V2 square over 2G into bracket 1 over CC minus 1. And we can factorize here now to also involve this that we know. P1 minus P2 over W will now be equal to V2 square minus V1 square. Oh, sorry. Let me write it separately because we have something else here. Minus V1 square over 2G, bringing this to the other side, minus V1 square over 2G plus V2 square over 2G into bracket 1 plus 1 over CC minus 1 square. And now, what do we know and what do we not know, so that we can substitute into the equation and get our answer? In the question, we're given discharge, we're given the D1 and D2. So we can find V1 and V2 from Q and a combination of D1 or D2. So now let us find our V1 and V2. So V1 will be equal to, we are finding it because we need it in this expression, V1, V2, to get CC. V1 will be equal to Q over A1, which is equal to 2 over 1 over 4 pi into bracket 0.2 square, and that will give us 1.91 meter per second. And then we have V2 is equal to Q over A2, which will now be equal to 2 over 1 over 4 pi into bracket 0.15 square, which will now be equal to 3.4 meter per second. You may be wondering, how did we get 0.2 and 0.15? Very simple. We are working in meters, so we converted this 200 millimeter and 150 millimeter to meters, dividing it by 1000. That's how we got that. So now that we have V1 and V2, what else do we need in this equation? We know, let me highlight the things that we know. We know this, we know this, we know this. That means that this CC is the only unknown in the equation, so we can easily find it by substituting. So now let us substitute the values that we know into that expression. So we have 0.655 is equal to minus v1 square, that's 1.91 square over 2 times 9.81 plus v2 is 3.4 over 2 times 9.81, then into bracket 1 plus 1 over cc minus 1 all square, and all square in total. So now I won't solve it step by step. I believe that this is just simple arithmetic. So basically, when you solve this further, you will get 1 over cc. When you solve this further, this expression further arithmetically, or however you want to solve it, you carry this to the other side, subtract, then divide. You solve it. When you solve it, you get 1 over cc is equal to 1.625. I didn't do it because that will make the video a lot longer, and that is just not what I want. So 1 over cc is equal to 1.625, and then when you find the inverse, you get cc is equal to 0.615, and it is a unitless constant. I hope it is clear. In the case of sudden contraction, there is a special case. If the entrance to the pipeline from reservoir is sharp, it is not rounded or bell-mouthed, it is equivalent to a sudden contraction from a pipe of infinite size to that of the pipeline, and the loss of head at that sharp entrance, HL, is equal to 1 over 2 v square over 2g, where v is the velocity in the pipe. Basically, when a pipe discharges into, or we can see the diagram, when this tank gives into this pipe, sudden contraction, when the reservoir discharges into a pipe, the head loss is this, and that is the special case in the case of sudden contraction. Thank you very much. In the next video, we'll be treating still losses of head, or losses in pipelines. I am Olunlade Joshua. Please let me know what you think about the video in the comment section below. Like this video and subscribe to this channel for more updates in the topic. Thank you for watching. I am Olunlade Joshua. Bye.